pleasure to have today Professor Christopher Deninger from the University of Muenster, who is going to give the second lecture in our series of lecture in selected areas of pure mathematics. So I'd like to give a short introduction to Professor Deninger. So he obtained his doctorate from the University of Cologne in 1982 under the supervision of Professor Kurt Meyer. In 1992, he shared the Gottfried Wilhelm Leibniz Prize with Michael Rapoport, Peter Schneider, and Thomas Zink. And in 1998, he was a plenary speaker at the International Congress of Mathematicians in Berlin. And in the 2012, he became a fellow of the American Mathematical Society. So Professor Deninger has been working in many areas of mathematics, in particular number theory and algebraic geometry, and also many other disciplines like dynamical system, functional analysis, and so on, topology. So his talk at the ICM was about the connection between dynamical system and number theory. And today we are very happy to have his lecture on zeta functions and cohomology. So the talk is going to be long. It's expected to be about 2 hours. So we'll have a short break in between after the first half of the lecture. So now, Professor Deninger.
Thank you very much for the introduction and also for allowing me to speak here. Yeah, since this ICM talk, for a very long time there was not much development, but more recently in the last years, there have been new ideas. And so the topic is the same as then, because I think it's still an extremely important one. The title is Zeta functions and cohomology. And the plan of the lecture is in the spirit of this lecture series to talk about the history of the problem and then just mention some famous conjectures on possible zeta functions. And then explain a conjectural cohomological formalism to attack such conjectures. And then discuss dynamical analogs. Analogs are done in the theory of dynamical systems, which look very similar to this homological conjectural formalism in a different context. And then I talk about the new things, dynamical systems for arithmetic schemes. And some of the properties. So the story starts maybe with Euler, but Riemann studied the zeta function, which was actually introduced by Euler in much greater depth in one article, this only article about number theory, objective number theory. And so, as you all know, the Riemann zeta function can be written as Dirichlet series. And in Euler's thesis, he proved for integral values of S that this has an Euler product. This can be factorized. And if you look at the proof, This statement is equivalent to the statement that every positive integer has a unique decomposition into a product of prime powers up to an order. This is equivalent to this equality. So this basic property of the primes is translated into an analytic equality. Euler did this first for s equal to 1. He makes the calculation that this is equal to this, and then he says both sides are equal to infinity, of course. Then he goes on for s equal to 2, 3, and says now it's. So we know that this holds in real part of s greater than 1, and it finds a holomorphic function there, which has a holomorphic continuation to C, to all of C except the pole of first order at 1. And the reason for the pole at s equal to 1, because can be deduced from the fact that the harmonic series diverges. And not have a pole at 1. And so from this fact that it has a pole, we can deduce. This implies that there are infinitely many primes. And this is the beginning of analytic number theory. So also special values, the topic of special values of zeta functions. It originated with a question by Mangoli in 1650, who asked about the value of zeta squared, zeta of 2, the sum of the reciprocal squares. And so this was answered, it was a famous problem, was answered by Euler 48 years later. And he showed that this is equal to pi squared divided by 6. So he did this in 1743, Euler. And he became famous because of this formula. And later he also showed that zeta of 4 is pi to the 4 divided by 90. And for all the even integers, we have similar formulas using Bernoulli numbers and powers of pi. And let's make a joke here. The fact that pi squared is not rational implies that there are infinitely many primes. Because if there were finitely many primes, and for s equal to 2, this would be a rational number, and this is irrational. It's a joke because I think the argument is strict. If you want to prove that this is not rational, you need to know that. Anyhow, it is very nice confirmation of the unity of mathematics. So people also thought about reciprocal sums over sum of reciprocal cubes, for example. So thought about zeta of 3. But this had to wait much longer until 1977, where Borel in a paper explains the nature of zeta of 3. I mean, by Aperi it was known that this number is irrational. But to understand it, he proved that this is up to a rational number, pi to the pi cubed times the Borel regulator of some element, so a rational number. Later also this rational number was explained, for example, by Bloch-Pato. And the Borel regulator is something that the regulator map, a higher Chern class map, from k phi of q, tensor q, then it becomes a one-dimensional vector space. It goes to R. And here we take a generating cycle, the basis of this one-dimensional vector space. So it's one-dimensional. We map it to R, and then we get a number well defined up to a rational number. And this is the structure. And this Borel regulator is a little bit like in the class formula where you have the regulator term, where you have logarithms of units. The units come from K1. And here, to understand theta of 3, you have to know something about K5. So similar formulas exist for theta 5, theta 7 in terms of algebraic K theory. This is a subject of special values, which was also developed very much in special values of the functions. Now, let us proceed with analytic properties of theta. So, the function has a famous function equation, and we need to complete the zeta function by an Euler factor at infinity, which is, strangely enough, this factor. And for later purposes, we also need another factor. This will be the factor for the real places, and this one for complex places. And one sets zeta ahead. Completed zeta function is defined as the ordinary zeta function, which is the product of these Euler factors corresponding to primes, which correspond to the non-Archimedean valuations. And then there's one more factor corresponding to the Archimedean valuation. That's this gamma r. So in the arithmetic sense, spec of V is not compact. You have to compactify by adding this infinite valuation. For example, the product formula for valuations holds only if you look at all valuations. So this thing is kind of viewed as compact. And if we want a good functional equation, we need to add this factor. Then the functional equation says simply that zeta hat 1 minus s is equal to zeta hat of s. Okay? And the analytic properties are zeta hat has poles of first order at s equal to 0 and 1. And zeros in the critical strip. So like this, 1/2. We have the symmetry by the functional equation, 1, and we take the mirror image here. The values at this point, this was the same, and also, by the way, easy to see, it's invariant by complex conjugations. And we have a 0 here, then this mirror image here will be 0 as well. So all the zeros lie in here, the poles are here in first order. And of course, the location of the zeros, this is a topic of the famous Riemann hypothesis, which said that, Riemann hypothesis said that if this function vanishes, then the real part of rho must be 1/2. So they should all lie on this line. So a lot is known about this. Wow, spectacular. This one? So for example, it is known that infinitely many zeros lie on this particular line, on this line, as was already proved by Hardy. And then up to first 10 to the 13 zeros are zeros of first order, and they also lie on this line. This is known. But the only 0, 3 regions in this critical strip have the form like this, where the boundary here goes asymptotic to the real line, the real part is equal to 1. So we don't have a 0, 3 region where you have fixed distance from the line. Prove this for any epsilon, smaller as it may be a huge advancement in the theory of prime numbers. So the Riemann hypothesis is very intimately related to the study of prime numbers. For example, we have the following statement. It is true if and only if for all positive epsilon, the function phi of x, the prime number counting function, minus the integral logarithm, is less or equal to some constant depending on epsilon, x to the 1/2 plus epsilon. If this is true, then you can have an even better estimate. And here, this is the prime number counting function. The number of primes below a given real number x, and Lie is the integral logarithm, dt divided by log. And in fact, there is a formula by Riemann which gives a precise formula as an infinite series over functions, and these functions contain the zeros of the Riemann Zeta function. So if you know where they lie, you get very good estimates and approximations. So these two things are good. Another formula which was also already observed by Riemann in a special case, and then put into a more modern language, more generalized, also to other types of Zeta functions by Weil, is the following. As distributions on the real line, Schwarz distributions, and for simplicity, we take only the positive real line. Yeah? Then the formula is somewhat simpler. We have the following equation. Now, this is an equation of Schwarz distributions. So these are linear functionals and test functions, compact smooth functions, compact support here. And okay, every local integrable function gives a Schwarz distribution. And now I write on the left the locally integrable function 1 minus these functions of t. We view them as distributions. And rho runs over the zeros of zeta plus et to the t. We view them, these are all locally integrable, and they give elements in d prime. This sum doesn't converge for any single real t. Yeah? It never converges, but if you view it as functions, but if you view it as existing as a distribution, then it's easily convergent. So we have this sum of distributions, and this is equal to the sum of the primes, log p times k greater or equal to 1, the right distribution in k times log p, plus the term which comes from the infinite place, which looks like this. This is also an integrable function, gives the distribution. A more precise formula is known on all of, as distribution on all of R. But then the infinite contributions are harder to write down. And also in this formula, you see that there is this is called explicit formulas because it makes an explicit relation between the zeros, zeta function, and the prime numbers. We will talk later about the analytic geometric meaning of such equations. In dynamical systems theory, there are similar ones, and you understand what they mean. So classically, maybe the formula, classically these formulas are written down using more explicitly. So if you have a test function in smooth function r greater than 0 with compact support, then the function, the distribution attached to this function, for example, does the following. If you view this distribution, you evaluate it, you evaluate on a test function by integrating over the test function. And then this formula reads as follows: phi. So then we introduce the function phi of s, integral from 0 to infinity e to the ts phi of t dt. It's an entire function. And the formula then takes the following more explicit form, looks like this: equal to sum over p's, log p, sum over k's. And now if you evaluate this on the test function, you just have the value of phi of k times log p plus the integral from 0 to infinity phi of t 1 minus e to the minus t dt. So this is a more classical way and more concrete way to write down this quality of distribution. Okay. So we see there are direct relations between prime numbers, primes, p and zeros, rho. And anyone who wants to study the prime seriously has to look at the Riemann Zeta function, that is analytic properties. So, except for the language here, this is much more what was already clear to Riemann. And there were generalizations, for example, by Deninger Zeta functions. So instead of Q, you study an algebraic number field. And I'm breaking it short like there is no more. And the zeta function of the number field will be sum over the integral ideals, 1 divided by the norm of the ideal into the S. And this will again be a product, have an Euler product in real part of S greater than 1, encoding the fact that every integral ideal can be written uniquely as a product of powers of prime ideals of ordering. So also here there were studies of special values. For example, we mentioned the work of Siegel, and for the odd, for the values of odd integers, again, Borel in the same paper. And before that, it was known that this function has an analytic continuation and also a functional equation. Functional equation for the completed zeta function, which is the zeta function times a real gamma factor for every real prime. So R1 is the number of real primes, and complex one for the number of complex prime places. And it's again a functional equation relating the values at S to 1 minus S. But this time they are not equal, but there is a certain factor in between. So the functional equation was proved by Hecker. Hecker proved the functional equation. And he used, for this, he used the theta functions and their transformation behavior. And wrote this, wrote the Dedekind zeta function, this one, as a Mellin transform. And so this proof, as we would say, is automorphic in nature. So this is an automorphic proof. Okay. Then there was another development, maybe in 1921. Emil Artin, wrote his thesis, where he studied an analog of zeta functions, not for number fields, but for algebraic extensions of a rational function field over a finite field. So this should be algebraic. And Artin looked at quadratic extensions where Q is algebraic equals in K. So quadratic extensions. So we know today that we have curve associated with this, and he was studying hyperelliptic curves over finite fields. And he also, then he defined the analog. In this case, you can make an arithmetic, speak of primary fields and places and so on, and which he did. And so he defined the zeta function in this context, and he proved that this is a rational function of p to the minus s. So it's periodic with a certain period in s, and it's a rational function. And he formulated the Riemann hypothesis for these functions, and he proved them. Proved the Riemann hypothesis, which takes the same form as for the classical ones, in 40 cases by calculation. And then the development was that Hasse proved Riemann hypothesis for zetas of elliptic function fields. Elliptic, so where the extension has genus 1. And oh, we looked at 40 extensions. He wrote them down explicit. Hard work. Check. Just check. 40 fields given by explicit quadratic equations, and it always worked. So Hasse proved it if this has genus 1, corresponds to an elliptic curve over Q, and Weil famously proved the Riemann hypothesis for zetas of all algebraic. Of all algebraic function fields. In contrary to Artin and Hasse, Weil was an advocate of the geometric method. He thought that working with fields was not a good idea. You should work with the curve. And in fact, so to the field, we have a smooth projected model curve over Fq. And from this curve, he made a surface x cross x over Q, and he used intersection theory on this surface and theorems about intersection. Theorems from the intersection theory of algebraic surfaces to prove the Riemann hypothesis for curves. So he introduced geometric methods into the subject. And there are two approaches to the ordinary Riemann hypothesis. One school tries to find proofs which are not geometric, which can be generalized correctly kind of, to the number field case. For example, there's this Bombieri Stefano paper, which really simplifies the Weyl group a lot, so one had the hope that one could transfer it to the number field case. And the other approach is to try to find a good geometry underlying some things like spec of Z, where one could actually approach the Riemann processes in a geometric way. And today I'm talking about such approaches. Okay. So secondly, this was history. Now, I don't know, I can give you numbers. Yeah. Did I give you numbers? Oh, we had no numbers. So now, let's pass to a higher dimensional generalization. So there's a zeta function called the Hasse-Weyl zeta function. Zeta x of S for any algebraic scheme over Z spectrum. So it should be separated and of finite type. Separated finite type, and then this is defined as the product of all the closed points of X, closed points. So if X is affine, this spectrum of a ring, they will correspond to the maximal ideals. 1 minus the norm of X to the minus S to the minus 1. That's the definition. Norm of X is the number of elements in the residue field. By the finite type assumption, the residue field by Hilbert's Nullstellen theorem will be a finite extension of the finite field if it's finite. That's the norm. It converges for real part of S greater than the dimension of our scheme X. And all the previous zetas are special cases. For example, if X is the spectrum of Z, then zeta X is just the ordinary zeta function. And if X is the spectrum of a number field, then zeta X is the Deninger zeta function. Because the closed points of spec of K correspond to the maximal ideals of OK, and these are just the non-zero prime ideals. These are the ones which I use the definition of the Deninger zeta function. And if X over FQ is a smooth projected curve with function field K equal to FQ of X, then function field K, then this Hasse-Weyl zeta function is this function which was introduced by Artin and studied by us in these field theoretical terms. So we have this nice higher dimensional generalization. Oh. So then the next step was in 1943, the Weyl conjectures. The Weyl conjectures, and I don't formulate them too precisely, but if X over Q is a smooth projected variety, then Firstly, the Weyl conjectures say that beta x of S is in reality a rational function Z of X in the variable p to the minus S. Yeah. Yes.
So, are there analogs of Hasse-Weil for those Haeckel functions?
You can guess. Yes. This would be.
I mean,
there's a
the
whole soup of Zeta functions.
L functions of Rosen characters.
Sure. Yeah, Grossen characters give rise. These are like Grossen characters give rise to motives, and you also have the notion of an L function of the motive. And there's an entire theory of this, and it has to be looked at in parallel. I don't want to speak about L functions in generality. It's too much to say. I stick to Zeta. But the L functions are important because the Zeta can be written as an alternative product of L functions of Hi cohomology and such. And you can study them individually. Yes. If these are algebraic characters, then you can make a motive for them, and the motive is a geometric object. In general, they belong to the homomorphic world. So the conjecture was that it is rational in p to the minus S, where this is, in fact, a rational function. And then he specified there should be a functional equation relating S, if S goes to D minus S. Yeah, so for our case of spec of Z, for example, dimension is 1, it is S goes to 1 minus S. Higher dimensions, it's S goes to D minus S. And the Riemann hypothesis in this case is that the zeros, respectively the poles of the Hasse-Weil Zeta function of such smooth projective variety have real part of S. So the zeros they lie in half integers, and the poles also in integers where the i's run from 0 to 2D, twice this dimension. And in the case of zeros, they are even. They are odd. And in the case of poles, they should be even. So for Riemann Zeta, for example, not for Riemann Zeta, but for curves over finite fields, which is a special case here, D, the dimension, so D is the dimension of X, is 1, so we're looking at I between 0 and 2, and the zeros should have real, and poles should have real part of S equal to I divided by 2. So zeros, there's only one part I, namely 1, real part 1 half, and even zeros are 0 and 1. Poles at 0 and 1. Should have real part from 0 to 1. In fact, this function is periodic in S with a certain period. And so this thing has infinitely many poles on the line real part of S equal to 0, and also infinitely many poles on the line real part of S equal to 1. So the formulation is even more precise, but I just say it like this. We studied this in this retreat, except Riemann hypothesis, all this was proved by Grothendieck school. Many people worked on this project, and using analytic cohomology. And the case, the rationality was proved by Dwarf in a very original paper using p-adic analysis, which is somehow a precursor to, say, crystalline p-adic methods. These L's are different from P. So rationality was first proved by Dwarf, and then, but it was also proved using analytic cohomology. But the Gutenberg school and also a functional equation comes from Poincaré duality and so on. And then in 1974, Deninger proved the Riemann hypothesis, the most difficult plot. And the proof does not use any kind of positivity. So while the second proof of the Riemann hypothesis for algebraic curves for finite fields used the positivity of the Rosati involution in the morphism ring of the Jacobian X, the ring of correspondences on X. It was really relatively simple proof using positivity in the scalar product which you can make from this. And Grothendieck's original idea to prove the Riemann hypothesis was to do something similar for higher dimension cycles and using the positivity argument. But and he formulated certain conjectures which are called the standard conjectures on algebraic cycles, which until now are unproven. They are very, very difficult. But if you knew them, then the Riemann hypothesis would be a very simple consequence of them, and you would in fact see why it is true. Deline's proof is very, very ingenious, and it proves it, but its positivity argument would be much simpler. Okay. So there are also later proofs after Deline, think by Lomont, using, I think, Kiel, using the Lomont Fourier transform, which are a bit simpler and different principles. I do not know any automorphic proof of the Riemann hypothesis for curved over finite fields. So these proofs are kind of geometric. So now, how do you approach these conjectures for the Grothendieck? What's the Grothendieck approach? So if you have some projected variety of LFQ, we set X bar base extension to FQ bar, and we equip it with the Frobenius, with the so-called geometric Frobenius, which is the Frobenius on X tensor, the identity. And then it follows from the left trace formula. In analytic cohomology for all powers of that. That we have the following cohomological expression for the Hasselbalch Zeta function in this case. It's the alternating product from 0 to 2D of the characteristic polynomial times the endomorphism of analytic cohomology X bar to the -1 to the I+1, so alternating product of characteristic polynomials of Frobenius. And note that this is a complex variable, and here we take an analytic vector space and determinants a priori with coefficients in QL. But in fact, these characteristic polynomials, they have coefficients in integer coefficients. So, and it turns out that they are not independent of the chosen elements. So we take these characteristic polynomials and insert this complex number, as you can do, and then you have this expression. And now the properties of zeta are reduced to the properties of the actions of Frobenius on analytic cohomology. For example, the functional equation. So rationality corresponds to the fact that cohomology is finite dimensional. Because then finite dimensional. That's its rational in B to the minus S. The functional equation corresponds to Poincare duality. And the fact that it is not S goes to minus S, but S goes to D minus S. The reason for this is that Frobenius does not act trivially on the top homology, but as P to the D, or in this case Q to the D, when he is the dimension. This is the reason for the shift. So that's a beautiful geometric explanation of the functional equation. And of course, zeros and poles, they correspond to the eigenvalues. Frobenius on analytic cohomology. Frobenius on HI X bar QL. And the Lin's theorem says that the eigenvalues lambda have absolute value q to the I divided by 2 on isomorphism. This is what, and then the real parts will be I, in S, will be I divided by 2. And this explains this. So we now, if we have this cohomological interpretation, then we have a complete understanding, or a very good understanding of the properties of the zeta function in terms of an action on cohomology. But you can also do other things with this. For example, this star, this equation, you can use it to study special values. We had zeta of 2, zeta of 4, and such things. Zeta of 3. Now you can, at least in this case, for varieties of Q, you also ask the same questions. Do the special values have some meaning? And so the star is also a starting point to study the order of vanishing. This is the first step of zeta functions as an integer, n, and the value, or more precise, the leading coefficient in the Taylor development around s equal to n. The leading coefficient in the Taylor development at n. This is the special value, this is the order of vanishing. So let me give a simple example of how you use this. You want to know what is the order of vanishing at s equal to n of zeta function. So by this formula, what you have to do is you have this order of vanishing is the alternating sum of the dimensions of the generalized eigenspaces. They are pure linear algebra. So the space, the algebraic eigenspaces, so I denote it by this tilde, for the eigenvalue p to the n. And now, by the wave conjunction, by the Wien's result on the eigenvalues of Frobenius, this is non-zero if and only if p to the n, if p to the n is equal to p to the I half. The eigenvalue here must have absolute value p to the I half if it appears on the HI. So this means that I is 2n. So the sum reduces, we have only one term. I is 2n, so this is what? Minus the dimension of H2n x bar QL. And then this part is algebraically equivalent to p to the n. And we want to express this somehow as something which is attached to the scheme X, which maybe does not know about all the Étale extensions of X. X bar, which you need to calculate the analytic cohomology. There's a conjecture, famous conjecture by Tate. You look at the n four-dimensional algebraic cycles, modulo, say, numerical equivalence, or conjecturally the same as homological equivalence in analytic cohomology. And then from here you have the cycle class. It goes to H2n X bar QL and goes exactly into this part. Where f star is equal to e to the n, true eigenvalue. And so the Tate conjecture says this is Tate conjecture. But this is an alpha-morphism. And then you need another conjecture, namely that the action of f star is semi-simple. To see that this would be same as the algebraic axis. And if these two conjectures are true, I mean, they are very difficult, mostly known for n equal to 1, then then you get the following expression for the similar law. It means it's not to say it's equal means no, it means the algebraic eigenspace. So f star minus p to the n times identity to some power of 0. I mean, it is conjectured that the action is actually semi-simple on such cohomologies of smooth projective varieties, but this is not known in general. It's a very difficult conjecture. But this would imply order at s equal to n of zeta x s is, so that all the minus dimension of a and x tensor Q, say. I forgot to say this, you have to tensor, in order that this be an isomorphism, you have to tensor with QL, of course. That's the Tate. And then you will get this interpretation. Yeah, it's the rank in this group. And then Tate also went on to show how from this, an analog of the Birch-Swinnerton-Dyer conjecture would follow in characteristic 0, in characteristic C. So this is the way, if you have a cohomology theory, this is the way to approach questions about special values. No? That's the, you have something wonderful to work with, obviously. And also the finite study, we have only talked about the order of vanishing, but you can also imagine that if you want to study the values, then this cohomological expression will also be very helpful. So finite study allows homological approach to understand the special value, a leading coefficient, the Taylor expansion of x that integers n. Okay. So this is a success story, except such things you cannot do in general nowadays. But in principle, this is the way to go. This is a success story. And we understand theta from a homological point of view. But now let's return to general algebraic schemes over C, maybe regular and proper or projective, which do not necessarily fiber over Fp, spec of P. They have more than one residue characteristics. Now you can ask, there are still analogs of the Bell conjectures. They are analogs of the Weyl conjectures. So this simple property you don't have. It's not a rational function. It's something simple, but you can expect to be an alternating product over entire functions of genus 1, or at least one, at most one, in general, and whose zeros should be similar as in this case. So they are analogs of Weyl conjectures. I formulated them somewhere, and I will recall some of them. And there are also very many conjectures on special values. Many conjectures of special values. Let's mention the names of the first, Swinnet and Dyer. Yeah, too many. Tate, Soulet, Bloch, Benison, Blockato, Lichtenbaum, of course, and Matthias Flach, and Baptiste Morin, and I have certainly forgotten important contributors are Fontaine, trying to understand special values and zeta functions more and more precisely. Not only on the rationals, first these were elliptic curves, later linear varieties, and then it goes to, this is vanishing orders, and then it goes to higher dimensional varieties with Bayesian and Bloch up to rational numbers, and Cato and Bloch up to units, and then Lichtenbaum also up to Lichtenbaum plus minus 1, and Flach Morin extending Lichtenbaum's ideas of contemporary in similar directions. So there's a huge amount of conjectures, very precise conjectures with no hope presently to prove any of them in general. Not even Muenster and Deninger can be proved in general, in spite of all the work. So here we have the Weyl. So this is a very unsatisfactory situation. But we have all these conjectures, and in special cases, modular curves, for example, certain Schmurrer varieties, complex elliptic curves with complex multiplication, they can be verified, or parts of them can be verified. And the calculations are very complicated, and they use the special situation, and for some miracles, two sides, theoretic, homological, becomes the same side as the analytic. But no one understands why. Deeper reasons. Okay, let us, I mentioned that there are Weyl conjectures about the analytic behavior of these Weyl data functions in general. So, first one is that zeta x of s has a meromorphic continuation to all of C. And it should be a quotient of functions, entire functions, which have a genus less or equal to 1 in the sense of complex analysis. So this is expected. And secondly, Serre has formulated a contextual recipe how to attach factors at infinity. So this will be a product of certain, I don't write it down precisely, it will be a certain product of shifted real, respectively, complex gamma factors of the type which we introduced, a certain product, and the recipe, how to do it, depends on the real Hodge structure. So the Hodge structure over R of, or let's say the Hodge structure of X, base dependent to R So you have a hot structure in the complex points, but you also need the action of complex conjugation. If you know all this is the hot structure, then he gives a recipe how many Euler factors to take and how to shift them. Purely empirically obtained. Let's call this X infinity. He also said, and then he says that if you define the repeated zeta function as Pascal zeta times these functions, and then there will be a functional equation with respect to S goes to D minus S. And he says precisely what the factor in this functional equation should be and how it is obtained. There will be a certain conductor, and he explains which one to take. It is all there conjecture. But not even the meromorphic continuation to C can be proved in generality. Whilst proved the Fermat conjecture, on the way he proved Shimura-Kanyama, who said that the elliptic curves of a cube are modular. And from this, you can use that the zeta function of a minimal model of the elliptic curve over Q has a meromorphic continuation to C. So this is again an automorphic. So this is known in this case, but if you write down take any regular, take any scheme, algebraic scheme over spec Z, you have no way to prove such a thing. No idea. All the proofs of this are the known proofs concern special cases, which are somehow related to automorphic forms. For example, certain Shimura varieties. When you get in relation to automorphic L functions, you can express it as a product of automorphic L functions, and you use their theory. And then you can prove 1 and 2 in some cases. But there is no geometry for this proof. First, use the Langen's proof. Now, thirdly, we also have the Riemann hypothesis part. And it says that for here also for the functional equation, I should make the assumption that X is projective and regular. And also here, so for projective, regular X, obviously, the same formulation as for smooth projective varieties over finite fields. Just the same. So the poles, zeros and poles of the general zeta function should have real part equal to I half, where I is between these numbers, so it's odd or even. And for example, in the case of the Riemann zeta function, can have it. There's no automorphic proof in any situation, I think, even over finite fields, of such a Riemann hypothesis statement. And even in the simplest case, spec of Z, it's the Riemann hypothesis for the Riemann zeta function. So we all know it's not proved. Okay. Yeah, we should make a break. It's a good moment to make a break.
So we are going to have a break. Anybody online have a question? You can ask question now if any.
Yeah, sure. Yeah, I think so.
So I just curious. So what is the automorphic wave conjecture? So I saw in the paper of Deninger. So after proof wave conjecture, he gave some application for Ramanujan conjecture, something that related to automorphic form. So I just asked, what is the automorphic wave conjecture?
No, what I meant was somehow to use to identify the zeta function, geometric zeta function, that via the product of automorphic L functions over function fields, and then somehow supply a proof for automorphic L functions of Riemann hypothesis, using some techniques which you can have in this representation theory techniques. I'm not aware of such a thing. That's what I meant.
Okay, thank you.
Okay, so we will have 15 minutes break, and we will resume at 15:20 Hanoi time. So 15 minutes. So we have kind of party right after the lecture. The process
Not so easy to cross the street. That is I will need some more chalk soon because I'm breaking it all the time. So I ended by writing down Bell conjectures for surveil data functions for schemes, algebraic schemes over Z, general algebraic schemes over Z. For example, the Riemann hypothesis for them just looks the same as for varieties over finite fields. Now, what is missing in the general case is a cohomology theory, global cohomology theory, yeah, with an analog of the formula star. The formula star said that the Hasselbalch Zeta function of a variety over finite fields is the alternating product of characteristic polynomials of Frobenius acting on cohomology, on analytic cohomology. And this formula was very, very useful to approach on this famous difficult to approach the data. So we don't have this explicit scheme over Z. And there are some obvious questions. First, there will be no periodicity in some variable p to the minus s in the global case. For example, for the zeta function, the zeta function is not periodic as it's almost periodic in some sense, but that's not enough. The periodicity in this function set made it possible that actually we had a finite dimension homology and took characteristic polynomial on this and then inserted this variable. In general, we cannot do it. Also. So the cohomology has to be infinite dimensional. But if it is infinite dimensional, the problem is what does a characteristic polynomial mean? Yeah? You have infinite dimensional, you have Fredholm determinants, but then this thing has to be compact. That's not obvious. So cohomology must be infinite dimensional. Infinite dimensional. But what are the determinants which you need for the characteristic polynomials? And so I found an answer to this a long time ago, and we need the following recipe. First, you define what the zeta regularized product is. So if we have complex numbers, not only many complex numbers, index set, then we said the zeta regularized product over the lambda nu is by definition the exponential of minus the derivative at 0 of the analytic continuation of the following Deninger series. If we do this if all lambda nu are non-zero, so that we can form this expression. And if this exists, I mean, firstly, this Deninger series has to converge somewhere on some right half plane and must have analytic continuation to zero. This is something that has probability zero, but we assume it happens. And it is zero if some lambda nu is to zero. So this is Zeta regularized product. And why do we do it? Note that if the index set is finite, then the Zeta regularized product is the ordinary product. Why? This is a finite series, so analytic continuation is no problem. So we may assume they are all non-zero. Finite series. We take the derivative, it gives you minus log of lambda nu divided by this thing. You substitute t equal to 0, you have sum over minus log lambda nu, minus minus cancels, sum over logs, exponential of this product of these guys. So if it's finite, it's just, I forgot to say, if you want to form this complex power of maybe complex numbers, we have to say where the argument lies. And we make the convention that it is greater than minus pi and less or equal to pi. This is an asymmetry, but which is necessary for the theory. You have to do it like this. And now, with this definition, some products make sense, which did not make sense before. For example, the Zeta regularized product over all the integers makes sense. The Zeta function in this case is the Riemann Zeta function. You take the analytic continuation, the derivative. This is known, and the result is root of 2 pi. By the way, in the works of Euler, you already find this formula. So he gives some other argument, but this he also arrives that this should be the regularized product. So this is an example where a product makes sense in this sense. And now define, we introduce a certain class of analytic functions, entire functions. So an entire function on C, polymorphic on C, complex value, is called Zeta regularized if we can write it, if it is equal to the Zeta regularized product over all its zeros with their multiplicities, and then we would take S minus rho over these factors. And in fact, for our theory, it is better because to get the good gamma factors to divide by 2 pi. So we take these things, they don't converge in the usual sense, but we say that they regularize if this is equal. So it means the spectral the zeta functions, the Deninger series, which you make with the zeros of your function, must have an analytic continuation, and you must have the fact that f of s is equal to this. Then we call it zeta regularized. And such functions have the property that you only need to know that are zeros with the multiplicities, and then you can canonically reconstruct the function. So I checked that this function is Zeta regularized. And also the real Euler factor, the gamma factor, as I wrote it down, and the complex gamma factor, all these guys are regularized. If you take this factor, then you get the gamma factors as I wrote them. If you take another factor, you get some term which complicates that. You get the simplest form for 2 pi. In this case, you can take any positive number, 1, you always get the same result. This is only necessary, or it's not necessary, but it is, you can omit it, but then you have more complicated factors. Slightly more complicated, nothing serious. So this is the best. So then I made some cohomological studies, and I thought that it followed, if the cohomology theory, as I imagined, existed, then the zeta function has to be zeta regularized in this sense. It must recover the zeta function from its zeros. And I should say that this is for all of our functions and similar for Merriam. On C, you take the zeta regularized product of the zeros, divide the zeta regularized product over the poles. And then you have a similar definition. Yeah. Maybe minus one, then they are holomorphic. Same thing. So then there was a theory developed by, well, I was there, and I proved it that Riemann zeta function is zeta regularized for real part of S greater than 1, and later Schröter and Soulet proved it in general and the entire plane. And then there was work by Cartier and Ubos on such questions, and by Jorgensen and Lang, such Lang. And maybe the best result is due to my student George Ilias. And these results say the following. I don't formulate it precisely. Understand it, then expected analytic properties, all local factors, this side, all local factors, there you don't have to assume anything, but also all Hasselbalch zeta functions and all completed Hasselbalch zeta functions are zeta regularized. So all these types of functions are canonically determined by their zeros and poles in this strange way. Also, even the classical formula that the Hasselbalch zeta function of a variety of finite fields is alternating product of characteristic polynomials, in particular tells you only if you only know the eigenvalues of Frobenius, then you already know the function. Not only up to a certain constant, but you know it. And for these functions, meromorphic in C, if you know zeros and poles, and usually you know the function only up to some nowhere vanishing holomorphic function. The point is you know them precisely. So this is a theory. So the other authors used the functional equation, and Ilias did not use it. Did not have to assume the functional equation. So in this sense, it's the strongest result. And now we can start defining determinants. So assume theta is an operator on, say, a topological vector space, complex vector space, and H, where you can speak about pure eigenvalue spectrum. Some theory. And if you have such an operator in such a theory, then you will define the zeta regularized determinant just as the zeta regularized product over all the lambdas in the spectrum counted with the multiplicity. Okay? That's our type of determinant. So let's give an example. 1 minus b to the minus s. I told you this is zeta regularized. This means it's a zeta regularized product over all its zeros. So when it's b to the minus s equal to 1, exactly, if it is a number of the type 2 pi I divided times new integer divided by log p. Yeah, so this is something which you prove, and it uses the very old formula from Lerch, from 18 something, on derivatives of Hurwitz zeta functions. It's a non-trivial thing, but you can use this work of Lerch. And now we want to write this. We want to write this as a determinant on some space. So we have to guess some space or kind of characteristic polynomial in this sense, not a polynomial, characteristic functions of some operator on some space. So we need an operator with these eigenvalues. And it's very simple. If you have eigenvalues, then you can obtain them as if you take a Fourier theory. You take the circle and the smooth functions of the circle, and they have bases into the 2 pi r nu. And under derivation, these are the eigenvalues. And dividing by log t means you have to change the diameter of the circle. So what you do is, take an obvious candidate is you do this, take this guy. So a better way actually would be to write this as r greater 0 divided by p to the z. And we need the operator. What is the operator? Theta is just d dt. And then the eigenvalues of this guy are these numbers. And because of this result, we have this formula. Now, another way to think about this, more geometric, this is a derivation. A more geometric way to think about this circle is a dynamical system under translation. You translate phi t of x as just x plus t. So t is in R, and x is on the circle. And the theta comes as follows. This is something on the geometry of the circle, and it induces an operator on this topological vector space. And you take, and its infinitesimal generator is the theta. So this is the infinitesimal generator of the induced flow on these functions. This is the way we think about this. Okay, so this is an example of Zeta regularized determinant. And one can make another space for the gamma factors, not so canonical as this one, and so on. So now we can write down the conjecture. About the cohomological expression. So for any algebraic scheme over Z, there is a cohomology theory with values in some type of topological C vector spaces. I'm not so precise about this type. Together with some operator, theta, such that the following homological representation for the completed zeta function holds. This should be the alternating product from I to 2D of zeta regularized determinant of 1 divided by 2 pi s minus theta and acting on hi. I will denote it by this. I view this as an arithmetic compactification of x, so where you add the fiber over the real numbers. Because here we have a completed theta function with coefficients in C. So this should be this type of cohomology theory. Should be a cohomology theory. We have no idea of what it is. Yeah? Just some space operators of this form. And we will later discuss what the geometric nature that this can have. And such a thing can only be true because of this result. Because this implies, so theta should have pure eigenvalue spectrum here and so on. This implies that this function is zeta regularized. Because this, by definition, is the zeta regularized product of 1 divided by 2 pi times s minus eigenvalues of theta. So if such a formula holds, then it implies that this is zeta regularized, which is a very non-trivial fact, but this is true. So otherwise, we could stop. And I have told you one example of the cohomology where we know what it is, namely H0 of spec of Fp in C. This is the thing that explains the zeta function of spec of Fp is just the Euler factor. Where is it? Yeah, zeta function is 1 minus p to the minus s inverse. This is the zeta function of the spectrum of Fp, and so we have seen that this is something like C infinity on log P. Z and theta is ddt. This is first until now new. So this is an example. Now we may know it. So then there's a theorem. In fact, for all varieties over Fp, such a theory exists. For all x over Fp, such a theory, cohomology theory with all good cohomological properties, also cohomological compact supports and so on exists. Yeah, I can construct it, but unfortunately not in a geometric way, like one would like to do, but proof formal start with étale cohomology. Plus Frobenius. Yeah. And then do something terrible, namely choose some embedding of QL into C. Terrible, yeah, terrible. Just shows that the theory exists. And then this becomes, you can view this pair as a moment. So you can view this pair as a local system on S1. A representation of fundamental group of S1. It's a local system on S1 or on GM, on C star. And then you use the Riemann-Hilbert correspondence, very simple case, and you turn it into a vector bundle with a connection. And the global sections of this vector bundle will be the cohomologies, and the connection evaluated in d dt will be the theta. And in this way, if you check them, you take the log, then the eigenvalues here will be all of the complex logs of the eigenvalues here. This one will be infinite dimensional. That's the sections of this vector bundle. Smooth sections. Smooth sections of the sheet. Right? The global sections of S1 of the vector bundle. It's infinite dimensional space. Oh. Yeah. If you take horizontal ones, then you can try to get back to these guys. That's true. Now, when you take all, it comes infinite dimension, it has to be. Because even in this case, as a function of S, this is periodic, so it has always infinitely many zeros and poles, and so infinitely many zeros, infinitely many different eigenvalues on these groups, so they must be infinite dimensional. That's one way to do it, so with cohomology, and more recently, Hesselholt The connection evaluated in DDT gives you the endomorphism. You need an endomorphism. So Hesselholt gave another construction of such a theory starting from topological cohomology. Which is not so artificial as this construction, but he also has to embed QL. So you see, such a theory can exist, at least in this special case, and the hope is that it exists in general. This construction using Riemann-Hilbert is due to Bloch, Spencer Bloch. My first construction was elementary, but he saw that this is a special case of Riemann-Hilbert correspondence. So now I will show you how to prove the Riemann hypothesis if we have such a formula, something we assume a hot start rate. So first we should say that now we can rephrase the Riemann hypothesis as the eigenvalues rho of theta on HI have a real part of rho equal to I half. Yeah, same as very similar in the case of finite fields, but this should be true in general. If we had such a theory, this is what we would expect. And now look at the completed zeta function. So let's look at x equal to spec b, completed zeta function. So it would be determinant on h1 divided by similar thing on h0 and similar thing on h2. If we have this, then the real values, the eigenvalues, the zeros here would have real part equal to 1/2, and here they should have real part equal to 0, real part equal to 1. So there will be no cancellation. So this must be responsible for the two poles at 0 and 1. And so this is so, then it implies that h0 must be C, one-dimensional, and eigenvalue 0 means that the entire operator is 0. H2 is isomorphic to C, but not canonically. Theta has eigenvalue 1 here because of the pole of theta head at 1. And so eigenvalue 1 on C means it's the identity. And so there must be some isomorphism like this. Call it the trace isomorphism as an entire convolution, for example. So now on H1, if we look at this formula, then the eigenvalues of theta on H1 must be the zeros here, so they must correspond to the zeros. Rho of zeta head. So now we know, we have seen our theta, the nature of our theta in our example. It's a very, very simple example was this is a derivation. And if it's a derivation, it must be a derivation with respect to cup product. And this here should have a cup product. So the cup theta of H1 cup H2 must be theta of H1 cup H2 plus H1 cup theta of H2 for H1 and H2 in H1. If they are in H1, then this will be in H2. But on H2, theta is the identity because of the pole at 1. So this is H1 cup H2. This formula implies that, and if you have a perfect pairing between H1 and H1, then it implies that if rho is an eigenvalue, then 1 minus rho is also an eigenvalue, which corresponds to the functional equation. But now we want more. Assume, let's be optimistic, that there is like for the Riemann, like in the cohomology of a compact Riemann surface, assume that there is an antilinear isomorphism. Antilinear. Such that if we make the following definition, H cup, that we get a scalar product, if we define this to be a trace of H cup star H prime. On a Riemann surface, you do get a scalar product. You have enough star operator, you get such a thing. Let's assume we have a star operator with this property. And we also have to assume that the theta commutes with this star operator. Now, if this is true, then the Riemann hypothesis follows. Yeah. Between H1, cup H1 to H2. I mean, they're infinite dimensional, so you have to say what it should be non-degenerate. Yeah. Okay, let us assume that this is such that this guy is a scalar product. That is a scalar product. Which means positive. Yeah. If your H should be positive, that's the point. Now then we conclude. And then this implies that now we take this formula here and substitute H for H1 and star of H prime for H2. And then on the left-hand side, we take a trace, which will be the scalar product. And here we will have theta of H1 cup star H prime. We take a trace. This will be scalar product, this guy. And here, similarly, except we have to commute the star and the theta to see that this is H theta H prime. Okay? We get this formula for the scalar products. And so this implies that theta minus 1/2. Yeah, we subtract 1/2 of this term and this term. So we see theta minus 1/2 is skew symmetric. And this implies that the eigenvalues of theta are purely imaginary. But the eigenvalues of theta are, if this is right, that are zeros minus 1/2. And this implies the Riemann hypothesis. And same arguments you can do in all dimensions for all varieties and so on. Now, of course, no one knows if positivity can explain the Riemann hypothesis. And people have different feelings about it. For example, I know that Bombieri does not believe it. I shared an office with Bombieri in Venice for 1 month. Peter Sarnak, as far as I know, also does not believe it. But I do believe it. And there's one heuristic reason why I think, which speaks in favor of positivity. You can do a similar thing for an elliptic curve. If you have an elliptic curve over Q, take the minimal model E, and then the same story should play out on this space. Should get a scalar product, and It should have a scalar product, using hot star operator and so on. And a little bit of this thing we know because the part where this is the one Eich's rate of this is where the corresponds to the the dimension of this is the vanishing order of the L function of E. And that should be explained by the rank of the model value. So what we do expect is that we have an isomorphism, which is, this is cycle plus from Homer. And this thing restricted to this particular space. I mean, we don't know if this exists. This is the take-type conjecture to this conjectural theory. But anyhow, it is, and this corresponds to something here. Here, the thing that it corresponds to is minus the height pairing. And this is positive definitive. So if this all fits together, if we have a tape conjecture in our setting too, then we can see a little bit of the scalar product, namely on this, especially on this part, it will be just the height pairing. This is something we know. Okay, so this is key, and there are conjectures on height pairings for higher dimensions. This fits, all this fits together very beautifully. So this is the only argument that I know why, which speaks in favor of positivity as a reason for the Riemann hypothesis. So, when did we start? The second session?
It was
So, already I spoke. Oh, just 35 minutes. Huh? Okay, that's good. Okay, so these things I knew for a long time, and I have thought about how to construct such a cohomology theory. This is, of course, the big issue. How can you construct such a thing? What is the nature of this? Do we have some geometric analog? Very recently, I noticed something which is important if one wants to construct such a thing. I had thought naively we can make some dynamical system and take a certain type of cohomology of this dynamical system, and this will be it. But one has to, the following theorem holds. A theory HI X bar C with operator, even so with standard cohomological properties, functionality and such things, even only for spectra of algebraic number fields, if we only have them for them, it cannot have a real structure. It's impossible to have a real structure. It must be a construction which leads to complex vector space. And the constructions which I have in mind, the dynamical systems always have a real structure. So this is not so clear. And this corresponds to something which was known for a long time. There is no Weyl cohomology theory in the classical sense for varieties over F bar set in R vector spaces. And this is a corresponding statement. And in both cases, some symplectic representations of the Nernst representations are the reason. The argument here is relatively simple. The argument here is more involved. It involves the study of the vanishing of Deninger Zeta functions that S equal to 1/2. But something better than C vector spaces is still a possibility. But a cohomology theory with values in the following tensor category, K index R, is an a priori possibility. Is possible, it's not excluded by this argument. So the objects are Z2 graded complex C vector spaces. So V has a degree 0 part and a 1 part, together with an anti-holomorphic, anti-linear automorphism sigma, whose square is -1. Now, whose square is -1 to the I, yeah, on VI. So, and then these are the objects, and morphisms are the obvious ones. And so in case the vector space has only 0 degree, then this means that we have a real structure on it. But if it has degree 1, then it only has a quaternionic structure. It doesn't have a real structure naturally. So it is known that for varieties over FP bar, there is a Bayes cohomology theory with values in K and KR, even a more refined category where it's graded, not only Z2 graded. And I had some communications with James Mill, who told me that Lodnik knew this. It is a consequence of the standard conjectures. So he knew that in this case, we had such a theory. And a priori, this is also a possibility for this theory, but real vector spaces is not a possibility. For example, over FP bar, if we take the H1 of an elliptic curve over FP bar, then this is degree 0. If E is ordinary, then we have something with a real structure, and it is degree 1 if E is super singular. So okay, now I will tell you quickly some analogies. From a completely different field of mathematics. So assume that we have a foliated dynamical system. So we have some space, we have some R action phi on the space, that's the dynamics, and we have some foliation. And F is one codimension. Foliation, and it should be transversal to phi, to the R action. This is a simple case. In reality, you will also need a situation for a good analogy where you have where it's not necessarily transversal. So why I'm thinking of this is a long story, but just assume. Yeah? Foliation means a partition of your space X into one codimensional submanifold, immersed manifolds. It doesn't have to, yeah, but they don't have to be submanifolds. For example, in the torus here, you have a real line which can wind around infinitely many times. And there are the refoliation. There are many things. But the foliation locally looks like a product. But globally, it can be very complicated. Now, define, in such a situation, define a sheet. C, that was respected by the flow, which means the flow should map leaves to leaves. And then we have a sheet C on X. So local sections are local functions, smooth functions, say. To C, such that which are locally constant on leaves. Now this is a complicated sheet. So locally, you will have very many functions. Because locally, a foliation is just a product. So that's just a product, and on the leaves, it should be constant. So it means just a smooth function on the base. It will be infinite dimensional always. But if you have a dense leaf, you look at global sections, then it implies that any global section will be constant. Because if it has to be locally constant on a leaf, but if it's dense, it has to be constant. This is a complicated sheet. And one can look at something, we can look at the cohomology of X with coefficients in C. And this will have an action of the flow. The flow will act. And it can act non-trivially. If you take the ordinary cohomology with C coefficients, it's homotopy invariant. If you have a flow, in R action, it's homotopic to trivial action, and so nothing happens. So if you want to see the dynamics on cohomology, you must do something more complicated. And the only thing I know, there is no general dynamically cohomology, because such a pair where you get some good cohomology theory with a non-trivial action, you need some extra structure. Foliation is one. And it has to be one-dimensional so that the formulas will become similar in number theory. I will show you something. So this can act non-trivially in general. And if you think about this, this is hard to understand. But this is the same as the harmonic I-forms along the leaves. They can make differential analysis not for the tangent bundle, but for the tangent bundle of the foliation. And you define what differential forms are, define operator and so on. And so this thing is isomorphic. There's a kind of Hodge theory. In fact, you need to take a maximum Hausdorff quotient, complicated. And these guys can be infinite dimensional, even for finite dimensional manifolds. Yeah. Yeah, T in R acts by the diffeomorphism by T.
And it acts along the family of each fiber. Is there one fiber to the other or?
Fiber? There are no fibers. The foliation. Yeah, there are foliation. There are trivial foliations, which are vibrations. Yeah? But the interesting ones are not vibrations. You have vibration over some base, you can look at the fibers, they form a foliation, but they are submanifolds. For foliation theories, these are the trivial ones. They are interested in foliations, but the leaves are dense. But in any case, the flow must, each phi of T at each time T must map a leaf. Again, this must be another leaf then. Otherwise, you don't have actually the cohomology. Yeah, it gives these 5 teeth always give diffeomorphisms between the different leaves. But they don't usually fix it. Okay. So I don't have time to motivate why I came to this geometric analog, but let me write down our formula. In such a situation, this is the Deninger, there's something like the Deninger complex along the leaves. Yeah? This is not an elliptic complex, but it's elliptic in the directions of the leaves. And it's very hard to say something about this or speak about index or something. But if you have the group action, the group action is transversal, then you have something like the transversal index. And there's a theory by Matthias, Sina, and Hermann. And here, it was made explicit, index theorem. And this is by Alvarez, Lopez, and Corduco. And it says the following. The alternating sum of certain transversal indices on such cohomologies. Yeah, these guys are distributions on R. Yeah, they are not numbers, they are distributions on R. And this is equal to a real number, von Euler characteristic times the direct distribution in 0, plus the sum over the periodic orbits of the dynamical system. And then comes the length of gamma times nu in Z, certain signs in direct distributions in K times L gamma, or nu times L gamma. Okay? If the codimension is higher than 1, you get certain quotients by determinants which you don't want. Only for codimension 1 it looks like this. And now recall the formula from analytic number theory. We have this 1 minus sum over rho, e to the t rho, yeah? Which is kind of, e to the t rho is something like e to the t theta, and this is theta, the infinitesimal generator, so this is phi t upper star, the induced action of cohomology. And so this is the trait of this, but the trait only makes sense as a distribution. So this corresponds to that, plus e to the t. And our H0 cohomology, the theta is 0, so it is 1. The trace in here will be this, and on H2 will be this. So this corresponds to this expression. And in number theory, I only wrote down the positive real line. If you write down the entire line, you get something like minus log discriminant over Q absolute value times delta 0 plus log gamma, log P. P runs over the prime numbers. And nu equal to nu in 0 minus 1. And then the direct distribution in nu times log P. And actually, here's a little problem that here we have P to the nu if nu is negative. So there's a certain, it's not precisely like this. It's a reflection of the fact that in this number theoretical analog, the space can never be a manifold. But you see, normally, yeah, these things look very similar. Lengths, so periodic orbits correspond to primes, length should be log of P, direct distribution here and here is the same. This is the topological cohomology characteristic. There's a theorem by Kohn, that Riemann-Roch theorem, which says the holomorphic Kohn-Euler characteristic, if you have holomorphic structure on the foliation, is 1/2 of this. So this will correspond to 1/2 of this, which is the log of square root of discriminant. And this number in Arachidov theory is called the Arachidov characteristic. So it corresponds beautifully with this. So you see, we have these kinds of analogies. And there's much more to be said. For example, the Lichtenbaum conjecture, certain Lichtenbaum conjecture on special values has a precise analog, word by word analog, as the so-called Green conjecture for the reality of the function. It expresses the value as a Reidemeister torsion, and in this particular situation, you can rewrite the Reidemeister torsion word by word as the recipe that Lichtenbaum gave in his paper. It is fantastic. Okay. And one can even prove that in the analogy, one can prove it. So now finally I will say something. So this was very short. It took many years to find these analogies and work them out. And anyhow, so the idea now is that maybe we should start with an arithmetic scheme and look for a dynamical system. And maybe with such a foliation structure or something in this direction, which will allow us to define a sheet and then hope for such formulas as the right cohomology. I should also say that Scholze, Dustin Clausen, and Peter Scholze are developing, so they have a huge program. They have been lecturing the last term on this huge program of analytic geometry over the integers. Together with a 6-factor formalism. Which means the best of all homological words is the right formalism to do homology. And actually, they also have they found an R action or the real numbers in their context, like we expect here now from the dynamical analogs. But they have not, they correspond to Peter, but they have not found the analog of foliation. So it's also not really a foliation, it's something in this direction. But I just also discussed this result, which somehow says that this global cohomology may be a vector, not spaces, but this kind of structure is something like a vector, like the vector bundle on the twister line, the real twister line. And I asked him whether in his theory he could also see something. And he said yes, even with a little modification, but we could communicate at this level. Very nice. So now let me sketch some. So now the aim is we start with an arithmetic scheme, try to communicate this construct a dynamical system from this construction of dynamical systems from an algebraic scheme X over Z. So my approach is relatively naive. I try to construct a space and so on. Hope the space is so small that I can see what the local, what kind of smooth or morphic or whatever functions, how they should be defined. Their approach needs to know what kind of functions you want, and then you make the spaces. Okay, so we need the concept of the rational limit vectors. In fact, I had constructed such a space without knowing about the rational limit vectors. And Peter Scholze explained it, and I still did not really understand. And then I understood the paper with Schorsek, and then finally I understood. So rational limit vectors is good. So let's take a commutative ring R. Then the rational limit vectors, so now we are doing some algebra again, completely understandable. Let's look at the rational limit vectors are certain power series, which can be obtained as portions of polynomials with a constant term 1. So P, Q, and R of T. And this quotient is taken in, we view them as, this quotient is taken in the big bit vectors, which are 1 plus T times R formal power series. Yeah? If the constant term is 1, then it can be inverted in here and then take this quotient. And so these are certain formal power series inside the big ring of formal power series. Now this is the big bit vectors, and they have addition. It's just the ordinary multiplication. And it has a product which I don't want to specify. Sorry, it's product which I don't want to specify. I only want to say that 1 minus alpha t times 1 minus beta t is 1 minus alpha beta t. And then this is extended in such a way that it's factorial. And there's only one way, and T radically continuous, and then there's only one way to make a product on these big bit vector rings, which has all the factoriality properties. And it turns out that the rational bit vectors in this sense are subring. Okay? And moreover, you have Frobenius and Verschiebung. Yeah? Frobenius and Verschiebung on these rational bit vector rings for all n greater or equal to 1. And also you have a Teichmüller character, a multiplicative map from R to the rational bit vectors of R, which sends alpha to 1 minus alpha t. By definition, it's multiplicative. It's not additive. Okay, there's a very nice way to think about these rational bit vectors as the so-called cyclic K theory. Cyclic K theory of R, which by definition is K0 of the endomorphism category of R divided out by K0 of R. So what is this? Endomorphism categories are pairs consisting of some projective finite rank R module together with an endomorphism. Yeah, you take here now the K group of these guys, their category. And here we divide out by those objects which come from M0 for the 0 endomorphism. We can take this quotient. And now we map this to the rational bit vectors as follows. So an element in here would be an equivalence class of such a formal difference. And we map it to the characteristic polynomial of phi divided by the characteristic polynomial of psi. Okay? M phi. This one, just a multiplicative map. A multiplicative map. It's not additive. Like in the vector theory. Yeah. Yeah, it's also called the Teichmüller character. So this is well defined. If it comes from 0 endomorphism, then the characteristic polynomial is 1. So this quotient goes to 1 here. And this is an isomorphism. That's the theorem of Muenster. And this gives a very nice way to think about the multiplication here. Namely, the addition in this ring is the ordinary multiplication. The ordinary multiplication corresponds to taking the direct sum of these guys. So this is a ring under direct sum. And as a tensor product, the tensor product is exactly what will correspond to this bit multiplication here. This is the way to understand rational vectors in a good way here. Okay, now we make a ring space. We start with a scheme, and we make a new ring space from it. It consists of a topological space. This is the underlying space of the scheme, but it has a new structure sheet. We take the rational bit vectors in OX. More precisely, we define a tree sheet, taking rational bit vectors of the sections, and then we sheetify in the Zariski topology. This is the basic, one basic geometric object. So now next one defines morphisms. Morphisms from the rational bit space of one scheme Y to the rational bit space of another scheme. And these spaces are not locally ringed. These sheets are not locally ringed. The local rings are not local. Sorry, the stalks are not local rings. And if we define a morphism, it's not only a morphism of ring spaces, but we need a locality condition. Like for schemes, one needs a locality condition. But I don't spell it out. But there's a natural one. And it turns out that if you have an ordinary map, F of schemes, then it would induce a map between the rational bit schemes. But this factor is only phaseful, it's not fully phaseful. There are many more maps on this setting, on this rational bit spaces, than more maps than coming from geometry. For example, we have Frobenius endomorphisms. On the rational bit space of any scheme, and they don't come from geometry. However, if X lives over Fp, then we have P Frobenius on X, and we have an induced map on the rational bit spaces, and this will be the Fp, which we always have. So in this case, the Frobenius comes from the geometric one. But these spaces have the advantage that they always have Frobenii. Even if this is speckled tree, we will have many Frobenii. So this is something very nice. These are we have Frobenius endomorphisms on the rational bit space for any n greater or equal to 1, in particular for P. And if it's defined over Fp, then the Fp comes from this one. Otherwise not. So they fit together. Okay, and this is the first type of morphisms which are defined. And I also define morphisms from a scheme to a rational bit space. And again, one needs these are maps of ring spaces together with a locality condition. And so in particular, we have S-valued points of X. They form the S-valued points of X. And there is always a canonical morphism from the scheme X to the rational bit scheme X. Completely canonical. And it implies that if the f-valued points of x, they sit injectively in the rational, in the s-valued points of this, of the rational bit scheme. Huh? But there may be very few points here, but many more points. For example, we can look at spec of Z and take the complex points of this. Completely useless, yeah, that's one point. And it sits in, now we take the rational bit space of spec D and its complex points, so meaning points with values in spec of Z, that usual. And this guy is infinite dimensional. And also, if we take this one point and look at the Frobenius orbits and all the Frobenius, we get infinitely many new points in this space from one. See, what we really want to do is we want to have a scheme and we want to take its complex valued points, and then we want to do analysis on manifolds on this and define our homologies. But it's not possible in the naive sense. But now we go to a different ring space and it has many complex points and also has Frobenia. So this is the last blackboard. For anyone who is interested in these constructions is invited to look at this, the long preprint on the archive, where you see everything in complete detail. But now let me just mention something. So there's a natural topology on W-rat XC. At least if the function field of X is countable if I don't define it in the generality, coming from the topology of C. Huh? So these guys are topological spaces now. They are, yeah. Then, special case, if F is a field containing all the roots of unity and of characteristic 0, then the connected components of W spec of FP. So spec of FP is just one point, yeah? But we make this construction, it becomes, then its C-valued points become something really big, a really big space made from a very simple object. And this guy is not connected to the topology. And any connected component is homomorphic. To the quadratic Schulze space. Maybe XF. Which they introduced in order to realize the absolute Galler group of this, whose at half pi 1 realizes is isomorphic to the Galler group of S bar or S. Yeah. So I spoke about this, and so they appear. So finally, let's construct the dynamical systems. So first, so we abbreviate the notation. The previous notation is abbreviated to this. This means new points of X, new complex points of X. So as I said, this has an action of Frobenia at every n. And it means that it has an action of the monoid of natural numbers. Positive natural numbers. And we want to invert it to get the group action. So we can do this standard construction. In this case, we have for the co-limit over this action. And then we can invert them all. Now we have an action of positive resonance. And the final step is to get the dynamical system is we take it and form the suspension with the positive real line, with the positive real numbers. multiplicatively. Suspension means we divide out diagonally. So it's the ordinary action here, and it's the action via the Fournier eigenvalue. This is a dynamic system. It has an action by R as follows: phi t of PU is PE to the TU. Now that's the equivalence class mod Q star, a pair P and U. And this is a dynamic system. Okay, then you show something. So the most important thing you show is that, to be honest, I need to make a certain restriction here, a certain subsystem, but I don't speak about this. But if you do it, then the closed points of the scheme, which go into the definition of the Hasselbalch Zeta function, they will correspond to periodic orbits, compact packets of periodic orbits on this space. So not an individual periodic orbit, but a packet, a compact thing, which is fibered over something and whose fibers are all the periodic orbits, and they all have the same length. So we have a closed point in our scheme. Then we have this packet of compact of periodic orbits, and they all have length log of NP, which you must have if you want to interpret the Hasselbalch Zeta function as a Rayleigh Zeta function for dynamic system. This is a basic requirement. And you have this in all periodic orbits do come from closed points. And the reason for this is the existence of Frobenius elements in Galois groups. So it's the best reason that can possibly be. And then one can show that these guys are connected and they're zero foliation. They have a kind of foliation because leaves are the images of this space across a point in here. Yeah? And then you can define a sheaf C of local functions, complex valued functions on this, which are locally constant on these guys. So we have the sheet, you can form the H0, and we can show the H0 is one dimension. This is a pretty trivial result, actually. It uses resolution of singularities in characteristic P federation theory, and also some approximation theories on the Adele system. Of course, we would like to calculate the H1 and hope that the eigenvalues are related to the non-trivial zeros of Zeta or Hasselbalch. The problem is that already the Schulze space have their own cohomology. The cohomology is something like the Q cohomology is something like an exterior algebra of F star tensor Q. And this reminds us of Milnor K-theory, but it isn't Milnor K-theory. The Steinberg relations do not hold in here. So their space is not the correct one, and they also say it in the introduction. And in the same way, the space which I construct is not the right one. It's not the right one, yeah? Maybe a certain subdynamical system will do the trick. I made a periodic level where the situation is better understood, and proved that there's a very natural subdynamical system if the scheme is spec of OK, the local field, and then the O-valued points in this energy, the subdynamical system will be in bijection to the points of the Fontaine-Farr curve, which is a very good objection. Yeah, so in that case, there's a very good subsystem. And my student Judith Lutz also shown in higher dimensions, in the periodic case, a relation between this subsystem and points of the diamond, which in the theory of Peter Scholz. So it looks good in the periodic analog, but we are interested in this case over Z. And here I do not know the correct definition of how to find this maybe subsystem or dynamical system mapping to this one. So I can only say this is a step in the right direction. I think it is a step in the right direction. Okay, all the details, and so I wrote something for the Georgie lecture, and this last part was a little bit more elaborate, much more elaborate than here. to get some impression. It's on the archive, and also this long paper, Dynamic Assistance for Arithmetic Schemes, which explains all these things in detail. Okay, thank you.
Yeah, thank you very much for very nice lecture. And we have time for some questions. Yeah. People online, if you have some question, you can post. I have some question. So the X at the very last, by the end of your lecture, is this a scheme characteristic P, yeah? Or do you have any assumption on X, on this curly X?
Nothing. That's the algebraic scheme over Z. Actually,
over Z.
these results are very important. Assume that X is normal. A normal scheme, normal algebraic scheme over Z. Now the point is that everything I do here works over Z. Yeah? I don't restrict to finite fields or something. We're not interested. We understand varieties over finite fields pretty well. And also over periodic fields. While these great advancements, starting with these perfector spaces of Peter Scholz and all this. This we understand. What we want to do is work over Z, spec of Z.
Yeah. And do you expect that your the theory, if it exists, specialized to analytic cohomology, or in some way when you take the fiber to FQ?
Well, the relationship would be the following. If not quite clear how it should be. In any case, this relation to analytic cohomology is only concerns the case where X is a variety over X or a finite field. Yeah?
I mean, you have X over Z, and then you take the fiber to FQ. Then, I mean,
yes,
does it specialize in some way to the analytic cohomology of the fiber?
Well, the cohomology of the fiber should relate to the analytic cohomology by this kind of Riemann-Hilbert correspondence, which I sketched at the beginning, which I mentioned. But if you have a global scheme like spec of Z, the analytic cohomologies, they don't give you of the fibers. It's just spec of P. You get nothing. But for spec Z, we already want an infinite dimension H1 with an operator whose eigenvalues is not trivial series. No way that we will ever get such a thing from analytic cohomology. Analytic cohomology sees finite extension, metallic extensions. Clearly, this is not good. This is, if you want to understand the Hasselbalch data functions, they are analytic. Yeah? They're not rational functions of something. They're genus one functions. And we need a generally complex value theory to cohomology theory and operators to deal with it. We cannot make a detour over analytic numbers.
Any other question? So these spaces, you have a foliation, but for infinite dimensional
that's
complex space. Yeah.
This space is too big, it's infinite dimension. Actually, in respect of E, what we really want is the dynamic system for X equal to spec of Z. The simplest case where X is flat over Z. The dynamic system X should be three-dimensional in some good way. Yeah. Why? If the cohomology is if the cohomology is something like a kind of foliation cohomology of this, then the cohomological dimension would be 2. And the cohomological dimension of foliation cohomology is the dimension of the foliation, the real dimension of the leaves. So the leaves should have dimension 2. But there should also be this flow transverse to it. So the entire dimension is 3. So this is what we want, and this is what we get.
In a bit too big, yeah. Okay.
This is also the entire cohomological dimension of spectral C. Maybe I mentioned one nice thing. There's this old idea goes back to Mumford and was written down by Maser, so developments from this. So he looked at spec of FP, it embeds into spec of C. And so topologically, this is 1-dimensional, and this is 3-dimensional. And also, this does not have any tau extensions, pi 1 and tau 0. So it's 3-dimensional, and it has a fundamental group of 0. So there's a joke. The Poincaré conjecture says this is something like S3. And this is something like S1. And this is an S1 embedded in S3. And this is a knot. So a class of such embedded is a knot. So primes and knots are somehow similar in some way. And there's a beautiful theory called arithmetic topology. And the world champion of this is Masanori Muneshita and Fukuoka, who has written a beautiful book about this, about these kind of analysis. So, for example, every knot has an Alexander polynomial. If you make exactly the same construction in this context, what you get is the Iwasawa Zeta function. The same, just the same construction. And then, for example, here with these knots, you can form a linking number of 2 knots.
Yeah.
Take a Zeta surface and you look how often it is intersected. And then the basic thing is this is symmetric.
Yeah.
And now here, what we have 2 primes. We can also find kind of a linking number, a quadratic reciprocity symbol. And it's something like this guy is -1 to the linking number. Correspond, huh? Okay, 2.
So what is the knot for 2? For the prime 2? What is the knot for the prime 2?
It's not so complicated. Yeah, in my dynamic system, you have periodic orbits for the prime 2. And you can see them. You can touch them. They are there. But in this analogy, not in S1, not in S3. And so the symmetry corresponds to quadratic reciprocity. Except quadratic reciprocity sometimes has a sign. It only works as P is congruent to Q, congruent to 1 mod 4. But the reason is actually this joke is not good enough. So it's some 3-manifold, and the knots corresponding to primes, they are homologically trivial only if they are congruent to 1 mod 4, otherwise not. That's the explanation why it's not completely symmetrical generally, according to Kaplanov and Smirnov. Also, there's something even there, more jokes. Actually, it's not a joke. There's a proof which works in topology and gives the symmetry, and in number theory, it is a proof of the quadratic reciprocity. You can translate this proof step by step. Morishita also, there's something here, 3 knots, K1, K2, K3, such that they are not linked. K1 not linked with K2, K2 not linked with K3. Then you can form something called a messy product. There are configuration of 3 knots which are not linked individually, but such that the whole thing is a non-trivial link. You cannot remove them. Messy products. I can make some pictures here. Like, I cannot draw it immediately. we can build some. And in number theory, so there's a method called, in number theory, there's some, for 3 primes, there's a so-called radar assembly. It was in the 1930s, introduced by radar to study certain quaternary extensions. And the construction of this guy and this guy, again, in this language, if you work out these analogies, is the same. So they're kind of method products of primes. And how does this picture fit in here? Well, the primes here should correspond to what I do in my construction, correspond to periodic orbits. If you forget the parametrization, the periodic orbit is just a knot.
Sorry. Okay, so if there are no more questions, let's thanks the speaker again. Okay, so we stop here. Thank you very much for your attention. And yeah, and now we go for a beer. Yeah.